Hello and welcome back to McGrathematics for your weekly dose of algebra. Today I'm starting off my series of integration videos aimed at advanced mathematics students studying the HSC called the Integration Guide. Today we're starting off with part 1. I'm going to show you what integration is and show you a few different types of questions. And if you are studying integration and feel like future videos may be of use to you, you should consider subscribing so you don't miss those. Okay, we're going to start off by talking about what integration is and how we integrate things. So starting off with what's called the antiderivative. So hopefully you've already studied in the advanced course and you know that 2x is the derivative of x squared. If that makes no sense to you, you should woo back and watch some differentiation videos first. Otherwise this is going to make absolutely no sense and waste half an hour of your life as well as mine. So 2x is the derivative of x squared. So we call x squared the antiderivative of 2x. It's differentiation, but in reverse. We also refer to antiderivatives as primitive functions. So when you see this terminology, you need to think integration. And the process of finding an antiderivative is called integration, which is what all these videos are going to be about. So let's move on to a question. Question is, can you think of an antiderivative or a primitive function for 3x squared? Can you think of something that when you differentiate it, the answer is 3x squared? If you are a super level genius, you might be saying to your computer screen, x cubed, when I differentiate that, the 3 comes down the front and the power becomes x squared. And you are absolutely correct. X cubed is a primitive function for 3x squared. However, x cubed plus 1, when you differentiate that, you also get 3x squared because the 1 will just vanish away. Likewise, x cubed minus 5 will also differentiate to 3x squared, and so will x cubed plus a million. So when we're finding an antiderivative or a primitive function, there could be a number on the end that's a constant that's plussing or minusing, and we don't know. So we account for that by writing our primitive function as x cubed plus c. All right, it could be 0, it could be a million. We don't know, but we need to have that constant there. Okay, so the primitive function of 2x is x squared plus c. Now let's talk about integration. So when we differentiate, as you're hopefully aware, we bring the power down the front and we reduce the power by 1. So we're reducing powers and multiplying. We are going in the opposite direction. We are integrating, so we need to do the exact opposite. Instead of reducing the power by 1, we need to increase the power by 1. And instead of multiplying, we need to divide. So that's why the integral, that's what this symbol here means. It's the integral, the antiderivative of x to the n. This dx means that x is the variable we are integrating, so we read this as with respect to x. The integral of this is the power of the x raised by 1, divide by the new power, and then add your constant as I explained before. Okay, so this is our starting point. Here's an example to show you how that works. We're going to find the antiderivative, or the primitive function, or the integral of 4x cubed minus 6x squared plus x minus 3. Starting with the 4x cubed, like I said, we're going to raise the power by 1 to 4, and now we're going to divide by the new power, which is 4. So we're raising to 4 and dividing by 4. For the next part, we're raising the x squared to an x cubed and then dividing by 3. This x is next. Now this is an x to the power of 1, so we raise that to an x to the power of 2 and then divide by 2. And then constants, when you integrate them, they get x's. You can think of this as kind of like 3x to the 0 because it's invisible. We raise the power to 1 and then divide by 1, which doesn't really do anything. So constants, when you integrate them, they just get variables. And of course, don't forget your plus c. Rule in my classroom is if you forget a plus c, you owe me 10 push-ups. So you need to do the same, otherwise I will find you. Okay, now we simplify this. 4 over 4 goes to 1, 6 over 3 goes to 2. So we can tidy it up to 1x to the 4 minus 2x cubed. This is still a half, and then minus 3x plus c. So that's integration in a nutshell. Let's do some examples and then look at some harder type of applications and then have a really great time. Here are our next two. Integral of x to the 4 minus 3x squared plus 4x minus 7. Let's dive right in. Starting off by raising the x to the 4 as an x to the 5 divided by 5. Next up, raise this 2 to a 3 and then divide by 3. Raise this 1 to a 2 and then divide by 2. The constant gets an x, and then there's a plus constant on the ends. Okay, that's the integration done. Now we can just simplify the 3 over 3 into a 1 and the 4 over 2 into a 2, and so we get our nice simplified answer here. At the front, you can write x to the 5 over 5, or if you prefer, you can write 1/5 of x to the 5. It means the exact same thing. It's up to personal preference what you prefer to look at. Okay, on the right here, we're doing the same thing, except now our variable isn't x, our variable is t, so that's why on the end it says dt. We're integrating this function with respect to t. So the 6 is going to raise to a 7 and then divide by 7. The 4 raises to a 5 and then divide by 5. The constant of 1 gets an x, so it becomes 1x, becomes 1t, pardon me. And then of course plus c on the end. And now simplifying, we can do 10 over 5 goes into 2, so we can make our answer a little bit nicer by writing it like this. Okay, so that's the idea, that's integration. So these were some easier examples. Everything was just very straightforward powers. Let's look at a more challenging type question with these spicy ones. First one is the integral of 1 over x to the 8 with respect to x. Okay, so to handle this, we need to write 1 over x to the power of 8 in a more calculus-friendly version, or otherwise known as index form. The way we can do that is by using negative powers and writing 1 over x to the 8 as x to the power of negative 8. Now we are ready to integrate this because it's in index form. Okay, so when we add 1 to minus 8, we get minus 7. So we're going to raise this to minus 7, divide by minus 7, and of course plus the c. This right here is a correct answer. You can make it look a little bit nicer if you want by putting the x back on the denominator with a positive power, and I like to put the negatives out the front because that's just what my OCD begs me to do. So we can write this as negative 1 over 7x to the power of positive 7 with the plus c still there. Okay, cool. Similar tricks over here. 1 over x to the 3, we are of course going to write as x to the power of minus 3. And writing the square root of x in index form, we can write this as x to the power of a half. Okay, so square roots are powers of a half. Now we can do some calculus. We're going to raise the minus 3 to a minus 2 and then divide by minus 2. Fractions get a bit tricky. When we add 1 to a half, we get 1 and a half, which we're going to write as 3 over 2. And then we divide by 3 over 2, and then we have a plus constant. Okay, again, this is a correct answer. It just doesn't look very good. We can make it look a little bit better. We can put the x to the minus 2 on the bottom of the fraction like we did over here. And when you have a fraction underneath your fraction, a cool little shortcut you can use is that the very lowest fraction, the very lowest number, which is the 2, that's going to flip up the top to join the x. We can also write x to the power of 3 over 2 as the square root of x cubed. Okay, so bottom number is your root and top number is your power. So putting that all together, we can say the x goes down below to have a positive power. We can chuck the negative out the front to make it look a bit nicer. The very bottom 2 flips up to join the x. The 3 stays down below. And x to the power of 3 over 2 is the square root cubed. And of course, plus c still hanging around. Okay, so these more complex examples are much trickier if you're not very confident with your index laws. They do get harder to tidy up. But yeah, you need to be pretty confident with index laws to really confidently work through these integrals. So if you need to work on that, that's a recommendation from me to you, free of charge. Okay, let's do a band 4 HSC question from 2014. We've got the gradient function of a curve, which is the derivative, is given by 4x minus 5. The curve passes through 2, 3. Find the equation for 2 marks. Okay, so here we've been given the derivative of a curve, and we're trying to find the original curve. So we're trying to go from f dash x to f. Okay, so we're trying to do differentiation in reverse, which is integration. So to start off this question, we need to integrate 4x minus 5 like this. Integral of 4x minus 5 dx. That's going to get us back to the original function, which is f of x. Okay, so integrating this, we are going to change the x to the 1 to be an x to the 2 and then divide by 2. The minus 5 is going to get an x to become minus 5x, and there is of course a plus constant. Now that's 1 mark secured. To find the other mark for this question, we need to figure out what c is. And to do that, the question has given us some extra information. The question has said that the curve passes through the point 2, 3. That tells us, simplifying here, 4 over 2 is equal to 2, of course. This point tells us that when the x value of this function is 2, the y value is 3, okay? X equals 2 gets us y equals 3. So to figure out what c is, we are going to sub in x equals 2. We're going to set y, which is the left-hand side, equal to 3, and then we can solve for c, pardon me. Left hand side is 3, letting x equal to 2, so we get 2 squared here and 5 times 2 here. Simplifying this, we get 2 times 4 is 8 here, and we get minus 10 here. 8 minus 10 will give us minus 2, and then move the minus 2 across the left to plus with the 3, getting us c equal to 5. All right, that gets us our final answer over here. With c equal to 5, we have 2x squared minus 5x plus 5 as the equation of our curve. Okay, beautiful. So that's integration. Now we're going to start looking at what happens with integration with limits, which are called numbers. Sorry, numbers which are called limits, and these are called definite integrals. Here is an example of a definite integral. We are integrating the parabola x squared, and we're integrating it between the values of 0 and 2. I'll show you what that means. We start out the same way by integrating x to the 2 by raising the power to 3 and dividing by 3. So that right there is our antiderivative. Now we use these square brackets and we put a 2 at the top and a 0 at the bottom. What this is telling us to do is we are going to substitute in x equals 2 and then subtract from that x equals 0 subbed in. Okay, I'll show you what I mean. Subbing in 2, we get 2 cubed over 3 for the first limit. For the second number, which is the 0, that always goes second, and we subtract. And so we're doing 0 cubed divided by 3. Okay, 0 cubed divided by 3 is just 0, so we're taking away nothing, which is not going to really do anything. So our answer is 2 cubed, which is 8, over 3. Okay, now the significance of this number 8 over 3 is if you actually looked at the parabola y equals x squared, and you looked at the area between the x-axis and the parabola, between the values of 0 and 2, you get this grey shaded area. Now the value of this area is actually exactly equal to 8 over 3 square units. Okay, this is one of the main reasons we use integration. We use it to find areas with weird boundaries. Okay, so integration allows us to find areas under curves, which we'll be doing a lot more of in a future video. Today we're just looking at how to actually integrate. So this is why we care about this. It's really useful. If you want to know how the integral gets that area, I strongly suggest looking up a better YouTube video because I'm not going to get into that today. It will take too long and I don't know how. All right, area is 8 over 3 units squared. Okay, so let's do some more examples with some limits. So here we have the integral of 3 over 5, and on the bottom we have x squared, integrating between 1 and 2. Okay, first little trick here is that when there are constants in your integral, if it makes your life easier, you can just put these constants out the front of your integral. So the 3 over 5, I'm just going to move out the front, and we're going to apply these to our answer later on just to save us on some working out. Because the x squared is on the bottom of the fraction, I can bring it up the top, and remember when you cross the line, you change the sign, so x squared becomes x to the minus 2. Now it's in index form, we're ready to integrate and then substitute in x equals 2 and 1. So raising the power, if we add to minus 2, we get to minus 1. So now we'll divide by minus 1. So that right there is our integral. We can tidy this up a little bit. I'm going to take the negative out the front and I'm going to put the x on the bottom of the fraction to make it positive, just to make it look a little bit easier to deal with. Okay, now like before, we're going to substitute in x equals 2. And then subtract from that, x equals 1 subbed in. Once we figure that out, we're going to multiply our answer by negative 3/5 because that's still out the front multiplying. So subbing in, negative 3/5 out the front, subbing in x equals 2 first, and then subtracting, subbing in x equals 1, looks like this. So inside we have a half minus 1 whole, so this is going to give us negative a half. And so we're doing negative 3/5 multiplied by negative a half, which works out to be positive 3/10. Okay, so that would be the area underneath this curve between these 2 points, probably. Okay, that's example 2. Let's do another one. Let's do example 3. Integrating between 1 and 4, x times the square root of x with respect to x. Okay, so first challenge here is to write our question in a form that's more calculus friendly. Trick I showed you before is that the square root of x can be written as x to the power of a half. So this is essentially our question. We can simplify this using index laws. When we multiply with the same base, our powers are going to add together. So 1 plus a half is equal to 1 1/2, which I'm going to write as 3 over 2. Now we are ready to do some integrating. Okay, this one gets a bit hectic. We are going to increase 3 over 2 by 1, which is going to raise it to 5 over 2. Okay, so adding 1 to this becomes 5 over 2. Then we divide by 5 over 2, and we've got our limits of 4 and 1. Okay, what we're going to do now is bring the 2 up the top. Like I said, when you've got a fraction under a fraction, the lowest denominator flips up to the top. And we can even put that 2/5 out the front. Okay, so 2/5 out the front, and then subbing in 4 and subbing in 1. So, and we're doing a minus because we do the top number subbed in minus the bottom number subbed in. Okay, you can put this through a calculator, or if you want to do this mentally, you can do the square root of 4 and then do that to the power of 5. 1 to the power of anything will always be equal to 1. So square root of 4 is 2. 2 to the power of 5 is going to be 32. So we're looking at 2/5 of 32, minus 1, of course. And so we end up with a final answer of 62/5. Okay, so pretty gnarly example. You got to know how to work with your square roots and combine your index laws, and then not be too scared by the fractions getting really gross and yucky. But that's calculus. Sometimes it is not beautiful, but it is beautiful to me. Okay, if you're feeling confident with that, I encourage you to pause the video and try these 2 by yourself. The first one is meant to be an easier one, and the second one is more challenging. If you're not there yet, you can just follow along with me and I'll explain it as I go. Okay, if you were trying them yourself, hopefully you've already paused. Otherwise, this is going to totally spoil it for you. First example, doing our integration, raising x to the 3 to x to the 4 over 4. X squared becomes x to the 3 over 3. And then 4x becomes 4x squared divided by 2. We'll simplify a little bit by just changing 3 over 3 to be 1 and changing 4 over 2 to be 2. Now, when we sub in our limits, we're going to put in 1s for x's and then take away subbing in 0s for x's. The convenient thing here is that when we substitute in 0 into all 3 of these, we just get 0 minus 0 plus 0. So the whole thing just turns into nothing, which is going to simplify our working out pretty substantially. So subbing in 1, we get 1/4 minus 1 plus 2. And then, like I said, substituting in 0, the whole thing just works out to be 0. Simplifying inside our bracket here, we end up with a final answer of 5/4. Okay, so not too scary. Okay, over on the right here, I'm starting off by writing it in index form by writing 2 minus x to the power of 1/2. So now we can do some integration. Integrating the 2 to a 2x and integrating our x to the 1/2. Raising the power to 3/2, dividing by the new power of 3/2. And now if we want, we can simplify a little bit. We can bring that 2 up to the top, like I said, same trick once again. And if you want, you can write x to the power of 3/2 as the square root of x cubed, like I said. Okay, so need to use pretty confident knowledge of fractional indices here to really get anywhere. Okay, let's make some more space. Now we substitute in 4, and it looks like this. Computer's lagging a bit. That's 4 cubed in there, that's 64. And then subtracting from that, substituting in x equals 1. 1 cubed, of course, is equal to 1. When we simplify this whole thing down, we get an 8 here. We get 2 times 8 here, which is 16. A 2 here and a 2 here. And then when we tidy the whole thing up and do all the subtraction, and again, this line right here can just be chucked straight into the calculator if you don't trust yourself. But we should end up with 4/3 as our answer if I did it correctly, hopefully. I should have checked these. Anyway, if I'm wrong, let me know in the comments and I'll send you a t-shirt, maybe. Okay, now an HSC question, a band 4 3-marker from 2007, so a bit of a relic now, but luckily calculus never changes. You can see the same questions from 40 years ago, as you'll see in your exam this year potentially. Integral between 1 and 4 of 8 over x squared. If you're feeling confident, pause and have a go. If you're not confident, let me do all the work for you. Okay, let's start off by bringing the 8 out the front. Like I said, constants out the front makes things easier. Writing 1 over x squared as x to the power of minus 2. Okay, now for the calculus, raising this power to minus 1 and then dividing by the new power of negative 1. Simplifying this a bit by bringing the negative out the front and writing this as 1 over x to make things look a little bit more beautiful. Substituting in x equals 4 and then subtracting x equals 1. So there's 1/4 minus 1 over 1. 1/4 minus a whole is negative 3/4. When we times that by negative 8, we end up with a final answer of positive 6. So if you got positive 6 and you tried it yourself, you're absolutely wonderful. I'm so proud of you, even if your parents are not. Well done. Okay, on to the next part. And to finish off for the last part of this first video, we are going to look at how to integrate using the reverse chain rule. So if you haven't encountered the chain rule for differentiating, I encourage you to watch my differentiation videos. Otherwise, again, this is not going to make any sense. But when we have a function to a power of n, the way we differentiate this with the chain rule is we bring the power of n down the front, we reduce the power by 1 as per always, and we multiply by the derivative of the inside, which in this case, the derivative of ax plus b is a. So that's why we're timesing by a. So when we're integrating something that looks like this, we need to do all those steps in reverse. So instead, we are going to raise the power by 1. We are going to divide by the new power, like we've been doing all video. And now instead of multiplying by the derivative, which is a, we are going to divide by the derivative, which is a. That's why a is on the bottom, because it's being divided. And of course, don't forget your plus c. So this is the formula we're going to be applying for the next few minutes. So maybe jot this down and we'll work through some examples together, starting off with these ones. Okay, integral of 3 minus 2x to the power of 5. So we're going to start off by raising the power to 6 and dividing by the new power of 6, as per always. So raise to 6, divide by 6. Already got my plus c there, but now the extra step, like I said, is to also divide by the derivative of the inside of the bracket. The derivative of 3 minus 2x is going to be minus 2. So we're going to put a minus 2 on the bottom. That's multiplying with our 6. Okay. I know this says times, but because it's on the bottom of the fraction, it's actually really dividing. So that turns the bottom into a negative 12. And that right there is our antiderivative for 3 minus 2x to the power of 5. Let's do another one. Okay, this one is more challenging because we have a fraction and we have a square root on the bottom. So we're going to have to put this into index form first of all. So we can write the bottom of the fraction because it is a square root. Once again, we can write this as a power of a half. And then we can bring this to the top of the fraction by changing the sign from positive to negative. So we can rewrite our question as the integral of 5x plus 1 to the power of negative half. There should be a dx there. I've just forgotten off, so apologies for that. So there we are in index form. Now we're going to apply our usual rules. We're going to add 1 to the power. We're going to divide by the new power. And then we're also going to divide by the derivative of the inside. So raise to a positive half, divide by a positive a half. The derivative of the inside of the bracket is 5. So we're going to put a 5 on the bottom. And hopefully I didn't forget my plus c. I didn't. Oh my God, I'm so good. Okay, so on the bottom, 5 times a half is going to be 5 over 2, but this very bottom 2, as before, is going to flip up the top to join the top, the numerator. Okay, so again, once again, when you have a fraction on the bottom of your fraction, the lowest denominator is going to flip up to the top. That's why the 2's moved up there, and the 5 is still down there. So we can also, instead of writing the top as a power of a half, we can write that as a square root to make it look a little bit nicer. And that there is our final answer. Okay, if that made sense, you are encouraged to pause and have a go at these two by yourself. Again, an easier one and a harder one. If you're not pausing and you're just watching along, here we go. Okay, for the first one, once again, raising the power to an 8 and then dividing by 8. Now, the derivative of the inside of the bracket is going to be minus 6. So we also need to divide by minus 6. So we've got raising the power, divide by the new power, and then also a negative 6 on the bottom with a plus c. So on the bottom we get negative 48 for our final answer right here. Now this next one's trickier because we have a square root and we also have some limits. So starting off by writing in index form as a power of a half once again. Raising the power, when we add 1 to this, it's going to become 3 over 2, and so then we'll divide by 3 over 2 as per usual. Also on the bottom, when I'm dividing, I'm putting a 2 there because 2 is the derivative, sorry, long day, of 2x plus 10. Okay, so raise the power, divide by the new power, also divide by the 2. Limits are 1 and 0. The bottom actually simplifies kind of nicely because the divided by 2 here and the times 2 are going to cancel out. So the bottom of the fraction is just going to turn into 3. And if we want, we can write the top as the square root cubed, because that's what a power of 3 over 2 does, square root cubed. Okay, subbing in our limits, so the bottom is 3, like I said. Subbing in 1, inside here we get 2 plus 10, and then subbing in 0, we get 0 plus 10. So making some space, and then simplifying a bit more, we're going to have 12 inside here, and we're going to have 10 inside here. applying our powers, like I said, square root cubed for both of these. We can combine them together into one fraction because the denominators are both 3. So putting it all together like this, that's a pretty good answer. If you wanted to evaluate the cubes, you get this, and then that's as far as we're going apparently. You can put it into the calculator and get a decimal if you want, but that right there is a pretty good answer. It's nice and exact with surds and a fraction. So if you pause and got that yourself, you're doing really amazing. That one's pretty tough, so well done. Okay, we're now going to finish off with some tougher examples and then look at some harder applications of the reverse chain rule, because these ones can get pretty hectic. This is a standard examination type question. Part A differentiates and then part B is integrate, and usually these are closely linked. So starting off with the function in part A, we have a function to a power of 5. So to differentiate this, we need to use the chain rule. So let's do that. Chain rule says the 5 comes down the front, and then we take 1 off the power to make it a 4. Now we need to multiply by the derivative of the inside. So if we differentiated this, we would get the 3 coming down to make -6, and the power becoming 2. So the derivative is -6x squared. That's what we need to multiply by, the derivative of the inside of the bracket. Okay, simplifying that, the -6x squared goes to the front with the 5 to become -30x squared, and that there is our derivative, which we're just going to write up here. That should say f dash x. So these are not the same thing. I'm just putting this aside so we can use it for part B. But this is the derivative of the question in part A. Okay, so now that we know that this differentiates to this thing in blue here, how can we use that to find the antiderivative of 10x squared 1 minus 2x cubed to the power of 4? Well, this looks pretty similar to the answer that we got in part A, except instead of a -30 at the front, we have a 10. So the trick with this question is, if we can manipulate our integral so that this question here looks like the answer that we got in blue, we know what this blue thing integrates to. We can find the antiderivative by just going back to where we started, which is 1 minus 2x cubed to the power of 5. So we're going to make the question look like this by turning this 10 into a -30 by multiplying it by -3. If I'm going to multiply by -3 inside my integral, I need to put a 1 over -3 out the front. Okay, so multiplying the inside by -3 and then dividing by -3 out the front. So I've kept the balance and I haven't really changed the value of the integral. Now we know the inside part integrates to 1 minus 2x cubed to the 5, and I've just noticed I've left the dx's off again. That's shame on me. Don't do that. You need to be better than me. So this integrates to the question we got in part A, the original function. And so there's our antiderivative. We can just keep the -1/3 out the front while we apply our limits of 0 and -1. So applying those, when we sub in 0, we get 1 minus 0 to the power of 5. That's just going to be 1. And then when we sub in -1, -1 cubed will be 1. Well, sorry, will be -1. So this becomes +2. So this becomes 3. So this whole thing turns into 3 to the power of 5. Okay, so again, -1 cubed is -1 times by -2 is +2. Add with the 1 and you get 3, and then we apply the power of 5. Hopefully that's not too hectic for you, advanced math students. You can handle that. Okay, so inside we're going to get 1 take away 3 to the power of 5, which is a really big number. The whole thing calculates to a final answer of 242 over 3. Okay, splendid. Let's try a pretty tough HSC question from 2019. It's a band 4, so we're getting up towards the higher end of the spectrum here. It's worth 3 marks, integrating between 0 and 1 of 1 over 3x plus 2 squared. If you've been nailing these questions so far and you want to try by yourself, please do, because that's the best way to get value from these videos and improve your skills. Okay, let's go through it. So first thing we're going to do is put this in index form. So we don't like the 3x plus 2 on the bottom of the fraction, so we'll move it to the top by changing the power to a negative. So rewriting this as 3x plus 2 to the -1. Now we're applying the reverse chain rule. So we're going to add 1 to the power, divide by the new power, and also divide by 3, because 3 is the derivative of the inside. So we got that 3 there. Cool. Okay, now we're going to substitute in our limits, or are we going to simplify first? We're going to simplify. Okay, so on the bottom we get -3. We'll bring that out the front, which is why there's a -1/3 there. That's the -3 on the bottom, yoinking out the front. Power of -1 puts this term on the bottom of the fraction, and now it just looks a little bit nicer and easier to substitute into. When we substitute in 1, we get 3 plus 2 on the bottom. When we substitute in 0, we get 0 plus 2. Okay, this whole thing calculates to 1 over 10 when we put this through a calculator, or you can do it by hand if you are just a lover of fractions like me. I appreciate that. But if you tried it yourself and you got 1 over 10, you're amazing. You got 3 marks, 3% of a 2019 exam question, like exam in total, sorry. Starting to ramble. I think I've been recording for too long. This is a long video. Okay, if you got this one correct and you think you are absolutely crushing this, you can try this harder one by yourself. This one's from 2011 and it's a band 4-5, so it's a little bit more tricky. Question that's very close to my heart because I actually did this question in 2011 back when I was a wee lad. So if you want to try this one by yourself, post your answers in the comments and I'll tell you whether you've got it correct or not, and we'll boost the engagement of the channel, which we love. Okay, moving on to the last part of the video, which is the harder chain rule. Looking at the version of the chain rule that's on the reference sheet, it looks like this. Where's my mouse? Here. It says when you're integrating a function to a power and that function is being multiplied by the derivative of the inside, you can integrate this by just increasing the power and dividing by the increased power. So basically, when you have a function to a power and it's being multiplied by its derivative, you can just integrate the function and this part will just vanish away by magic. You can see this by differentiating the right hand side and you'll end up with the left hand side, so it does work. I'll show you how we use this in a couple of questions and then we'll look at a hard recent HSC question. So here are the tougher examples that you are much less likely to see in the HSC, but it does happen, so we better cover them. Okay, first one, our function is 1 minus x to the 5 and that's being raised to the power of 10. Now the derivative of the inside is minus 5x to the 4 because the 5 comes down, the power becomes 4. So we really want out the front of this bracket to have a negative 5x to the power of 4 so we can apply this property. So the way we're going to fix that is we are going to put a negative 5 inside our integral, which means we need to divide by negative 5 out the front like this. Okay, so we've manipulated the question so that in front of our bracket we have the derivative of the bracket, and now we can just integrate the bracket as per usual. So raising the power to 11 and then dividing by 11. And then when we divide by the derivative of the bracket, it's just there and it vanishes. So it works out really nice. So we keep the negative 1/5 out the front, raise the bracket to 11, divide by 11 and plus c, and that's our final answer. So a bit trickier, but once you get the hang of this sort of pattern, you can evaluate really scary looking integrals in a much easier way. Similar idea over here, we've got 2x cubed minus 7 raised to a power of 3. The derivative of the inside would be 6x squared, and here we have a 5x squared, so we want this 5 to be a 6, so we can apply the same pattern again. So we'll just, oh yeah, simplifying this, sorry, that turns into 55 on the bottom, but yeah, you know that. Okay, putting the 5 out the front, like I said, we want a 6 here, so we have the derivative of the bracket at the front of the bracket. So we put a 6 there and divide by 6 out the front, and so it's all nice and balanced. So that again was the 5 going out the front, putting a 6 inside, and then a 1/6 outside. Now we can integrate this by raising the power to 4 and dividing by 4 with a plus constant. And now we just simplify by doing 6 times 4 on the bottom gets us 24 with a 5 on top. So we have 5 power of 4 over 24 plus c. Okay, so the reason I have to teach this is because in the 2023 exam, they threw in this really hectic band 5 question using this formula. So 2 marks, so it's not a lot of work as long as you know what to do. Let's go through it. First thing we're going to do is change the square root to be a power of a half, and now we have a function to a power, so we want to apply the reverse chain rule. The derivative of the inside is 2x, so we want to have a 2x here, and we can make that happen by putting a 2 there and then putting a half out the front. So this is really just a 1. Cool, now that we've done that, we can just integrate the bracketed term, raising the power up to 3 over 2 and then dividing by 3 over 2 as per usual. This 2 on the very bottom, as I said before, is going to flip up the top, and then 2 times a half is going to make 1. So this half here and this 2 down here are actually going to cancel out really nicely. And then we end up with, on the top, we have a power of 3 over 2 again. So once again, that's the square root cubed, which I've got here. got our plus c, and the 2's cancel out, and we end up with just 1/3 out the front of the square root cubed because of the power of 3/2. So yeah, pretty tough. If you're getting these correct and you're understanding what's happening here, you could be a Band 5 student and heading towards a really great result in your HSC. Okay, that was a lot. Well done if you stayed along for the entire thing, and hopefully now you're a little bit better at integration. And if you stay tuned for the channel, next week I'll have another video looking at integrating exponentials, logs, and trig, and then later on we'll do some applications. But that's all for today. So thanks for watching along. I hope you're learning, and I'll see you in another video hopefully soon. Bye for now, not forever.